Hey guys, welcome back to Cougar Chem Tutoring. I'm Austin. I'll be running through part 2 of problem set 16, molecular orbital theory. So in the last video, we looked at our very first molecular orbital diagram and filled it in based on the valence electrons that came from the molecule that we were looking at. And we were able to predict bond orders and magnetic properties, and we're even able to look at the electron configuration based off of the orbitals that the electrons were in. So if you have questions on that, I would refer you to the last video. But for this one, we're just going to kind of go through and look at what a typical question like this might be answered typically. And I only have one of the examples in here from your problem set, but I feel like this will give you a good headway into actually solving the rest of these on your own. So first, all you have to do, you never have to produce this diagram. It'll always be given to you, at least for the sake of Chem 105. Just figure out how many valence electrons you have. So they're asking us to predict the MO structures for CO plus and NO minus. So we're actually going to have to compare these guys. So we're going to predict the bond order for both of them. I'm going to say bond order here. CO plus would be this, and then NO minus. Okay, CO plus, we got 4 plus 6 minus 1, right? Because we've got this plus charge here. So it's going to be a total of 9 valence electrons. So I'm going to put 1, 2, 3, 4. And then remember the Hund's rule. So we got to put 3, 4, 5, 6, 7, 8. Okay, and then 9 right there. So that's going to be, if I'm looking for the bond order, remember it's bonding minus anti-bonding over 2. So that's going to be 2, 4, 6, 7. So that's going to be 7 minus, and then just 2 over 2. So that's going to be 5 over 2, which is 2.5. That's a pretty high bond order, right? It's not quite a triple bond yet, but it's getting there. And it's paramagnetic, right? We've got an unpaired electron up here. So I'm just going to go ahead and say this is this is magnetic. And we'll compare that to NO minus here. So NO minus, I'm going to fill this in with a different color now. Okay, NO minus. NO minus. So now we've got a total of 5 plus 6 plus 1, right? So now we've got 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so now I've got 2, 4, 6, 8. 8 in bonding orbitals and 2, 4 in anti-bonding orbitals. So that's going to be 4 over 2, which is just 2. So I'm going to put a 2 here, which is just a double bond, right? And we've got these unpaired electrons up here. If you had paired these up prematurely, then you would have probably said that this was diamagnetic. But this is actually paramagnetic because these two guys are separated. So this is also magnetic. Now, in terms of the weakest bond, if we're looking at this guy right here, the weakest bond, I'm going to expect that the weakest bond has the lower bond order. So that's going to be NO, okay? And that the shortest bond, okay, the shortest bond is going to be the one with the highest bond order, right? So that's going to be, oops, I'm going to put it right here. That's going to be CO plus because it has a higher bond order, okay? So that's a kind of a typical compare and contrast that they may give you between two molecules using molecular orbital theory, okay? All right, so now it says, using MO theory, explain the difference between a conducting metal, a semiconductor, and an insulator. So I want to show you this diagram because it's going to help you a lot. I feel it helped me a lot, at least when I was first trying to understand this. This is really just an application of a molecular orbital theory, where if we have one sodium, right, sodium's a metal, right, and typically when we're looking at these things, we're usually looking at metals or semi-metals or things like that. So remember that when we combine two sodiums, we're going to create a bonding and an anti-bonding. And if we put 3 of them in there, we create another one up there. And then you can kind of see how this just continues to get greater. And when we're on the level of like moles, right, we're 6.022 times 10 to the 23, you can see that this is going to get extremely complicated and very big, right? And so what ends up happening is we create what we call bands, okay? And these bands, this band up here is actually what we call the conducting band or the conduction band. Okay, and the one below it is the valence band. Now, the valence band is typically filled with electrons, right? We've got all these electrons down here because electrons like to be in lower energy level orbitals. And then this conduction band is pretty much empty antibonding orbitals, right? They're all antibonding orbitals. Valence is filled with bonding orbitals. And this is all entirely based off of molecular orbital theory. If you remember in the very beginning of class, when we talked about bonds in general, we talked about metallic bonds, right? And we said that there was like the sea of electrons. And we said that we would kind of elaborate on that later. Well, this is where we're doing that. What we're saying here is that there's not necessarily a sea of electrons, but they are able to move like a sea of electrons. Because if these electrons down here get excited enough, kind of like when we were working with the photoelectric effect, or even just Bohr's model, right? We were talking about exciting electrons up here. Well, that can happen with heat or with electricity or with whatever it may be. If we knock an electron off, we can actually bump it up and it can conduct through. It'll come up and come right back down, but it'll transfer that energy to the next guy. He'll come up, come right back down, come up, right back down. And you can kind of see how it's just going to kind of keep moving. This charge will just kind of keep moving across a metal. And so when the conduction band is close to the valence band, when they're kind of touching like this or overlapping, that's when we have conduction, because that makes it easier for these electrons to jump up and then jump back down. If there's a greater distance to get there, it's going to be a lot harder for it to conduct electricity or heat or whatever it may be. And so what you'll end up seeing like on tests and stuff are things like this, okay? Metals or conductors, right? They usually have this overlap between the valence band and the valence band and the conduction band. Semiconductors, which are they're kind of on the metalloid side of the periodic table. They can also be alloys and made up of several different things, but they actually have a very small gap. Now, this gap does cost energy to cross. However, it does cross it sometimes. If it does, it can jump up here and then come right back down. In fact, our phones are dependent on semiconductors. In fact, a lot of technology is dependent on semiconductors. They actually like having this particular thing, because if we just perfectly conducted everything, it actually wouldn't work as great as we'd like it to. So this would be a semiconductor. The bigger the gap, though, the more it turns into what we call an insulator. An insulator would be something like a styrofoam cup, right? We actually want things like styrofoam to stay insulators, because if we had hot chocolate and we had it in plastic are pretty good. Plastics are pretty good conductors, unfortunately, of heat at least, not necessarily electricity, but of heat at least. And so that heat would get to our hand really quick. But styrofoam is really nice because the gap between the valence band and the conduction band is so high that the heat doesn't necessarily transfer all that well. And so this is how we use molecular orbital theory to describe conduction or the lack thereof in certain materials like metals, semiconductors, and insulators. Okay? So as far as the test goes, I think that's the extent that you would need to know. At least thus far in the year of 2021, fall of 2021. Maybe they'll add some stuff later on, but as far as these videos go, from what I've seen on tests of applications of molecular orbital theory, I think this is the extent of which you would need to be able to explain or recognize this kind of stuff. All right, last one, number 6. It says acetylene or ethine is a highly flammable hydrocarbon used in welding because of the extremely high heat temperature of the flame produced. Below is the molecular orbital level MO energy level diagram for the C-to-C bond in acetylene. Now, let's go ahead and write this out to kind of see what it would look like, right? So I'm going to say carbon is bound to carbon, and then it's just 2 hydrogens, which must mean that there is a triple bond here because carbon has to make 4 bonds, right? So, okay, that may help us later when we're looking at this. So A says, knowing that each carbon atom is using one of its 4 valence electrons to form a sigma bond with a hydrogen atom, fill in the MO diagram for the C-to-C bond. Okay, so what it's saying here is typically, carbon has the 4 bonds here, 4 valence electrons, I mean. And then 3 of these are being used for the other carbon, okay, to make these triple bonds, but 1 of them is being used for hydrogen. So now what they're actually asking us to do is only fill in this MO diagram for just the C-to-C bond. So that means that there is 1 electron in each of these orbitals. Now, you may be wondering, what the heck is this orbital right here? Well, this is actually combining valence bond theory and molecular orbital theory, because this is a hybridized orbital. This is going to be the sp hybridized orbital. Because if you look at the steric number, right, steric number is 2 on this carbon, and so it's going to be sp hybridized, and when we mix an s orbital with a p orbital, it's going to mix, whoops, it's kind of an ugly looking p orbital. It's only going to mix with one lobe of the p orbital, and then we end up getting this kind of funky looking lopsided orbital, because this orbital ends up adding up to greater than the other side. So you can see where this is coming from, right? And so they're actually combining both theories, which is kind of funky. We actually end up doing this. Maybe you may end up doing this. Some professors don't actually teach it like this, but you may end up doing this in organic chemistry. So I'm actually going to put one electron in each of these because that's what hybridization does for us, right? It spreads it out so that we can have each orbital partially filled so that we can make a bond. So when I fill these in, I have a total of 6. I'm going to put 1, 2, 3, 4, 5, 6. Now if I take bonding minus anti-bonding, I have 3, 2, 4, 6 right here, right? 6 minus 0. There aren't any electrons in antibonding orbitals. Divided by 2, that's going to be 3. That's a bond order of 3. And that makes sense when we look at the actual molecule, right? The molecule shows that I have a triple bond. And so we can actually use the Lewis structure to kind of verify, how well does our molecular orbital diagram and the bonding order that we get from it coincide? How well do they relate to each other? And in this case, we're able to verify it. Part B says now they want us to label the molecular orbitals. Well, hopefully you can kind of tell that sigma is always going to come first, at least in terms of in terms of S sigma or sigma S, typically that's going to come first. So I'm going to put sigma down here, and then its corresponding antibonding orbital. Notice that these lines follow each other. Okay, so those are going to be the sigma and a sigma antibonding. And then pi will you always have 2 of them. Okay, so that's kind of key. There will always be 2 pi because you always have 2 other p orbitals that aren't making any other bonds. The other p orbital was made to use this hybridized orbital that then can make a sigma bond. So I'm going to put the pi down here and then the pi star right there. Now they're asking us, is it paramagnetic or diamagnetic? So I'm going to fill this back in. This is diamagnetic, right? This is going to be diamagnetic because all the electrons here are paired. And we already determined the bond order. That's going to be 3. And now E says, during the combustion of acetylene, the carbon-to-carbon bond is broken. Should it take more or less energy to break the carbon-to-carbon bond in acetylene than ethane? Or than in ethene. Okay, so earlier in Chem 105, they actually required Chem 105 students to understand or to know organic nomenclature. So you technically don't know what ethane is. Ethane is just C2H6, and then ethene would be C2H4. And so the Lewis structures for these actually look like this. So we're going to get C, I got 3 H's on this guy, and then 3 H's on this guy. And then here I've got the Lewis structure. I'll just put a line, or even just box this guy. And then over here, this would actually be a double bond between the 2 carbons. Okay, so they're asking us to compare this to this structure that we wrote over here. So would it take more or less energy to break it in acetylene than in ethane? It's actually going to take more in both, right? More in both because the bond order is 3. I'll just put this over here. Bond order is equal to 3. Okay, so the higher the bond order, that means the stronger the bond, right? And so that's going to make it harder for us to break it. So in either condition, whether we're comparing it to ethane or ethene, it's going to be because the bond order is 3 as compared to 2 or 1, it's going to be a lot stronger. Okay. All right. Last question. It says, what is the difference between hybrid orbitals? We're right here, just in case you're lost. What is the difference between hybridized orbitals in valence bond theory and molecular orbitals of molecular orbital theory? Well, remember that valence bond theory, these are atomic orbitals, right? Atomic. We hybridize these guys, and we said that these are unique to this atom, right? Carbon had its own sp3 hybridized or its own sp2 hybridized, and all the bond was overlapping hybridized orbitals. It's I compare valence bond theory to molecular orbital and the molecular orbital theory in the following way. So valence bond theory, I say, is like singles holding hands, right? Really, all they're doing is they have their own lives, right? So, but all they're doing to connect is holding hands. Okay, so this is like valence bond theory. In molecular orbital theory, if you're religious, I call it the marriage one flesh theory. It's kind of a scripture quote. So marriage one flesh theory. So MO theory. Where marriage is not so much just holding hands, it's like becoming one. And so they actually become their own whole new orbital. It's like a whole new entity in and of itself. And so valence bond theory, we're talking about, atomic orbitals, where in molecular orbital theory, obviously we're talking about molecular orbitals. And that's really the hugest difference between the two. And it ends up being a lot more accurate when we're talking about molecular orbital theory. So it's really interesting that we actually end up seeing or end up understanding molecules in terms of the MO theory instead of the BB theory. Also, MO theory gives us more insight into anti-bonding orbitals, which VB theory does not give us insight into. And actually, this becomes really important once we start getting into organic chemistry, because anti-bonding orbitals actually kind of explain why reactions happen. By placing electrons into an anti-bonding orbital, we break a particular bond, but then we use that to make another bond, or so on and so forth. So that's also another thing with which it can help us. But all right, well, I hope that was helpful. I'll be making a review for exam 2 in the next video, because at least up until fall of 2021, this is where the material for exam 2 stopped. So I'll see you there.